Hello everyone. So I will switch it over. You can see the data mining project, and we're gonna get right into it. So first off, I'm just gonna explain what's happening. This is once again the first running of the data mining project, and so not the first running, the first version of the data mining project. So this was the version that was successful in its initial run, but since then I have run it to completion essentially once. There was somewhat of an error at the end, which caused me to have to stop the running that was actually almost successful at the end of the last stream. What happened was there was an error when the deep list is attempting to update in order to acquire the variables that have been implemented in the new best programs. This is a problem that I fixed in later versions, but I didn't fix that before I started running this because I wanted it to be untouched. But then I realized that that's kind of stupid because that doesn't really help the process. But so I fixed it, but it essentially required me to restart the program anyways. So I just ended that running and began the next one. Now I can go tell you what the best score was in that circumstance. So let me get down to the bottom here. The best score was actually, I want to read it to you. It was 6. It was on the scale of 6 million, whereas the normal fuzz scores are around 11 million and up. So that means that they're a little bit more significant than so this score was about half of those, and that's usually what it starts getting at when it starts getting to a better equation. Now the equation that was associated with that was the variable 2 times variable 4 plus variable 1 plus the quantity of variable 4 times variable 1 plus variable 5 minus variable 6. And so this last term in the parentheses, variable 5 minus variable 6, isn't really important, but the rest of them are pretty important because variable 2 times variable 4 is something that happens, variable 1 times variable 4 is something that happens, and those terms being added together is something that happens in the equation. There's an extra variable 1 in there, but that's not too significant for the shape of the equation. And so the second equation was very similar, except for that last term that was variable 5 minus variable 6 was just one variable, and that variable was variable 1. So both of these equations show promise of having of being better and getting to the actual answer, but like I said, there was that error that occurred when there was some deep learning trying to happen, and it wouldn't allow it because there was too much. The problem was that the way it was set up, the program could only really add in one variable at a time. So if two variables came up and both of them needed to be added in, then it became problematic, and that's what happened. If you run something for a long time, even a small probability of an event happening tends to add up into where it actually does happen. So that's the situation. Right now, the current best program has a score of about 12 million, and the equation is variable 1 times variable 4 plus variable 4. So there's a lot that's good about that, but it does have some work that needs to be done. The second equation is actually the same equation, which, as you'll remember, was a problem with this version of the data mining project. Now, you may hear some dog barking in the background. I think my girlfriend's sister just came home, but we'll just keep moving on. So that's what's happening. It's not much new, but I did mention in the previous stream, if you want to go listen to that, about a possible new alternative to the genetic process of that I'm attempting here in order to achieve the data mining project. So I want to make sure I'm in the frame. But that's pretty much it. So I'm going to move into my topics for today. And I do have full topics today. And those topics are logarithms and the Alfred-Kinsey scale. So I'll be explaining those more when I get to it. But for now, I'm just going to go straight into my first topic. So I'll give it a second, and then I will begin logarithms. Okay, so, and just as a reminder, if there's anything that I mention when I'm going through an explanation here, feel free to ask questions if you don't understand, and possibly if you do understand but you think that other people might not understand, bring that up and I can go over a specific section a little bit in more detail. So today we're talking about logarithms. And I'm going to redraw that M. And so the big thing with logarithms, that the reason that I wanted to talk about it is because it seems like a lot of people that aren't in math-oriented situations, like if in the arts and whatnot, a lot of people who just have a maybe Algebra 1 or college algebra schooling on math tend to just not understand logarithms. And I mean, that's nothing on those people. It's just that logarithms aren't necessarily something that we use on a daily basis. So it's not, people tend to not really get a grasp on it when they're initially taught. So I just wanted to kind of explain it in hopefully a new light compared to what people might have gotten in school. So essentially, first off, let's start with a math problem that's pretty simple. So if we have a problem that is some number, so we're going to say 7 to the 2 equals what? Okay, so this is a pretty simple math problem. We have a number, we're squaring it or putting it to the power of 2, and we want to know what the answer is. So most people can square numbers, or it's pretty easy to do on a calculator. So this is 7 times 7, it's 49. And that's what this equals. So this is a pretty simple math problem, but this is a power function. So if f of x equals some number to the x, that's a power function. And so and then f of x would be our answer. So what logarithms are is somewhat of the same thing, but a little bit different. And what I mean by that is it's a confusing topic because we're not necessarily talking about an entirely new topic from this equation. We're actually just moving where the question mark is, essentially. So a logarithm is basically saying 7 to the what equals some number, equals 49. And so this would mean that the answer is, the answer we're looking for is actually the power that we're dealing with. And the way that this problem would be written out in a logarithmic syntax is log base 7 of 49 is equal to 2. And so this means that 7 to the power of 2 equals 49. It's the same thing as this equation up here, but it's a little backwards, and that seems to be where people tend to trip up. So this is an interesting idea because this means that this logarithm, log 7, is actually the inverse, or the, I guess you could say the inverse of 7 to the x. So if we have log 7 of x, right? And we multiply that by 7 to the x, then, sorry, I'm doing this wrong. If we have log base 7 and we take the log base 7 of 7 to the x, then we should get x, right? Because if we have, this is essentially uh, log base 7 of 7 squared. So this would be our x term, and it becomes the answer. So that's basically what a logarithm is, and I want to explain a couple cool things that you can do with logarithms. So with a logarithm, like I said, you can have really any base. So here's the base, here's the number you're applying it to, and here's your answer. So this base can be anything you want it to be. But what you'll see is on a calculator, if you were to be using a logarithm, then you would usually see two things. You'll see log and you'll see ln. And so I'll just explain what these are right now. Log is actually log base 10. This is just something that is used commonly. It's usually kept on a calculator. I have mine here, and you can see, well, actually, it's kind of scratched off, but this button right here says log for logarithm, and then right under it, it says ln, and ln is actually log base e. And so then you'd be asking, what is e? Well, e is actually the Euler number. If you know the number pi, it's somewhat like that. It's just a constant that comes up a lot in math that we use. This is actually equal to, I believe, 2.718 ... as in it continues on forever just like pi does, and there's no repeating pattern to it. So log base e is the natural log, because e actually comes up a lot in natural occurrences, but there's some cool things about e. The derivative of e to the x is so de to the x over dx is equal to e to the x, and it's the same for the integral. Its slope is the same as the position that it's at. So it's a little weird, but so these are the common things that you'll see, and that's what you can use on your calculator usually. Now, some fancy ones, if you get the Inspire or the TI Inspire or anything like a TI 89, they tend to have a log base function where you can plug in whatever base you want. But there is ways to use other bases when you only have a simple calculator. So if you have log base 10 to work with, then so this is just log. So what you can do is there's a change of base formula. So if you want to have your log base 7 of 49, but all you have is log base 10 to work with, then what you can do is you can say log of 49 divided by log of 7, and that should be equal to your answer. I'm actually going to try that out for myself just to make sure that I'm not blowing smoke here. Divided by log of 7. So that gives us 2, which is what we said that the answer was. This works out because there's some funny stuff that happens when you divide logarithms. It's actually somewhat like subtraction in a sense. I might have that backwards, but I'll save that for another day. But this is basically what I wanted to talk about on logarithms. So if there's any questions, I'll either answer them before I get into the next topic, or if I see them late, I'll answer them at the end of the stream. But with that being said, I think we're going to be moving into my second topic, which is the Alford-Kinsey scale. So I'm going to clear some stuff up and get another sip of water. All right. So this is going to be somewhat of a different topic, but as you would see from the title of the stream, everything I'm talking about today is about relationships. So I talked about logarithms, which is the relationship between power functions and its inverse, which is a logarithm. And so it's sort of like asking a different question in a sense. But this next part, I am going to be talking about sexuality. And so, specifically in the realm of psychology, there is a somewhat simple scale that was created by a man named Alfred Kinsey. And so this scale, I'm just going to draw it out, but essentially it's somewhat of a rating of someone's sexuality in terms of their heterosexuality. So I'm going to try and write sideways here. Failing. Heterosexual and I'm working on it. Okay, that may look bad, but okay. So, and then there's these boxes and a line, and then 1, 2, 3, 4. Is that enough? 1, 2, 3, 4, 5, 6. Yes, I believe so. So 0, 1, 2, 3, 4, 5, 6. And there we go. Let me see if I've successfully colored or completed these lines. I have not. People who have seen my random drawing section, which I will be doing in a little bit, I'm terrible at finishing off these lines. So we're going to color this in. I'm so close. Okay. So we have our... Dang it. We have our scale here. And so as the orange grows, then that would mean that someone is to more of a homosexual orientation than a heterosexual orientation. But there are these values in the middle that are somewhat even. So this is basically it was the first accepted understanding of sexuality. So what happened in psychology is for a while, homosexuality was actually considered a mental illness, as in they had there's a big like guidebook to mental illnesses and mental disorders, and homosexuality in some of the original copies was considered a mental disability almost. And so obviously as society progressed, we've evolved that realm of knowledge into a more accepting community. But so this was one of the first sort of exceptions of the idea that there's some gray area. Now, obviously, only having 6 options is still being somewhat categorical. So it's still categorizing people into boxes. And the thing with science and with more logic-minded people, they want to group people together because it's easier to some sort of, I guess, deal with. Well, okay, let's think about it this way: demographics. So obviously today we are pushing to have a more accepting society that's more fluid, in a sense that there's less racism, there's less pointing out of the fact that people are different. Okay, so people are always going to be different, but that doesn't necessarily make people unequal in a sense. So that's what society's pushing towards, is this idea of equality. But at the same time, when you go into concepts of marketing and economics, creating demographics is a very efficient way of projecting your ideas and your products to people that may be interested in those products. So let's say that you have I don't know, let's say it's a Sears commercial for grills. Those commercials tend to come out in football games and maybe big sporting events, and the reason for this is because they're attempting to reach out to a male demographic. Now, it is very widely understood that not that the viewers of sporting events like football aren't just male, but there is a very high percentage of males in that demographic that is watching a sporting event, and there's a high percentage of males who are interested in grills. So obviously there will always be some gray area, but statistically speaking, you can group people together in a sense. Now, I will say that this scale is somewhat limiting. So let's say, so basically to explain it, there's a box here that's completely blank, and this means that this box is representing completely heterosexual. I was reading up on this before I started the stream, and essentially, the original sort of test for where someone fell in this scale was actually how many sexual encounters a person would have with a given gender based off of their gender. And so this would be someone who has only had sexual encounters with the opposite gender. Now, since then, the scale has been opened up a little bit more to just because obviously there's people that may have thoughts and desires that don't necessarily match their actions. So since then, this scale has been opened up to a little bit more abstract, subjective understanding. But at the same time, psychology today doesn't really necessarily go by this scale anymore, because we understand that that grouping people together into individual categories isn't the best for describing the individual. So I think is that's working. Okay. Okay. So the thing is that today we are now starting to understand a lot more that when you maybe on a macro scale for something like providing a product to a group of people that may be interested, creating categories, creating brackets, creating demographics does work, and it may offend some people in a sense that maybe there's someone who really hates grills that's watching a football game with their friends, and they don't like grills at all. But statistically, it works on a macro scale. But when you get down to the micro level of the individual, or perhaps a small group of people, you can't put people into individual categories, because you don't get that picture of the individual characteristics of a person and how they feel on the inside simply from some statistic like how many men they've been with and how many women they've been with in relationships. So I think that Kinsey's idea of creating this category was a good step for psychology, because when uh, when this chart came out and when this graphic idea came into existence, it sort of opened people's eyes to the idea that there isn't certainty, there isn't an analog nature to this. There isn't just heterosexual and homosexual. There's an entire spectrum in between. So um, there's a bunch of different categories in the middle where maybe someone is completely half and half, which we call bi, or there's in total. There's so many different names for um, the sexual orientations that people accept for themselves. But even people within those specific categories uh, can feel completely different about how they view sexuality. So I guess this is just something to keep in mind when talking with people in society today, because the world is changing, and things that were acceptable in creating understanding in the past don't necessarily meet the standards of today's society and the diversity that we now understand is out there. Um, so that's pretty much what I wanted to talk about on Alfred Kinsey. I do like having these psychology topics. stream. Psychology is a topic that really interests me, and it felt like having a psychology topic would be a nice counter to the math topic before of logarithms. So I'm going to be moving on into my final section of the random drawing. I have my stuff out already. I guess I finally learned, but I want to thank you if you're still watching already, or if you're watching this on the if you're watching this not live. So I'm going to get this all set up, and we will move into the random drawing. Okay, so you guys know the drill. I have my paper here. Is that still? I think the mic is screwing up. Is that working? Nope. Hello? 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 Okay, I think that one's working. Sorry about the lack of professionalism. I'm hoping that the end of the last section wasn't too hard to hear, but I know you can still kind of hear what I'm saying when that happens. I need to get a new cord or something for my mic. But, okay, so now we're starting the random drawing section. So you guys know the drill. I have my paper here. I'm going to get my random number generator up on my calculator, and we're going to go 1 through 25. And our first number is 1, which is mouse. That's the noun. We're going to go again. We have 10, which is intermingle. That's pretty on par with today's topics. And finally, we have another 10. What are the odds? I believe 1 in 25. Or I guess to get two 10s, it would be 25 squared, which would be... I'm not going to do the math at the second. Solid. Okay, so as opposed to those hollow mice that we have in the past, we now have a solid mouse. So I guess this idea of being solid could be, let's say, a little bit more abstract. I guess to go along with the ideas we've been talking about already. So maybe this idea of being solid just means that there is something on the inside. So if we have our mouse, we can start with a circle and kind of extend it out here, and so we have that kind of looks like a duck at the moment, but I don't know. We're still working on it. No, I'm going to start over. That looks a lot like a duck or a donkey, or I don't know. Okay, so if we have a mouse, mice have these kind of round ears, and then they have a round off face and big eyes. That looks so ugly, but okay, so we got this tail, and then mice have pretty strong back legs. I saw a video actually from a college campus where they would actually train rats to jump from one thing to another. It was sort of like an Olympics of rats. And the rats were actually pretty smart in learning the different things they had to do. But this is a mouse. Mice tend to be a little bit more clean, I guess. They're more welcomed as pets, but they are a little bit on the smaller side, so I guess that would make them a little less athletic. But perhaps this rat is actually intermingling with this is a mouse. And so this rat, being a solid character, is not the hollow shell that is seen on the outside, there is something to this rat. This mouse. So maybe this mouse does not wish to live by the standards of its society, in which it cannot compete in the Rat Olympics. Um, so it's going to the Rat Olympics because it understands that it has characteristics that live up to a higher standard than the category that it has been put into by society. So the rat is going this way, and the mouse is going this way. But I guess we don't have to call it a mouse if it doesn't want to be a mouse. So we have our young, solid, standing citizen going to the Rat Olympics, striving for gold. Maybe the size will inhibit its ability to compete for a medal position, but at the same time, that doesn't mean that it should be ruled out, because this mouse is worth more than it's seen on the outside, I guess. I don't know. So I think this is a pretty good picture. This rat is maybe 0.5 rats, which would mean that it's half the length of a rat, and maybe 0.3 rats. And in terms of volume, it would be around maybe 0.002 canoes. I did say that I was going to make a push for this being an actual volume measurement, or it could be a measurement of amounts of things, but I guess that would also be in terms of average volume. So this picture is pretty complete. If you are a mouse that wants to compete in the Rat Olympics, please post your story in the chat. I'm sure people would be very open to hearing that. There seems to be a large community, so those people are #relatin, just to throw that in. Oh, I think I spelled that wrong. I'm sorry to anyone that may offend. #relatin. Okay. That's a homage to anyone who knows what that's from. But I think we're done with the picture here. So I want to thank you guys for watching. I didn't go as long as I was planning. I guess I'm getting a little better at leaving less blank space in the middle of things. But once again, thank you guys for coming out. I want to just mention that I'll be streaming on Wednesday. It will be another just update. I'm not sure. I might actually do a cover song. I've been working on a few songs that I have in mind. So if that's something that you'd be interested in, post in the chat or hit me up on Facebook about what you want me to play. But other than that, I'm going to be continuing the running of the data mining project that I have going here, and attempting to work on that alternative method if I can get some inspiration on how to do so. So other than that, I will be signing off, but I will see you on Wednesday.